Hello, everyone. So today we'll be covering chapter 21. Uh, Let me just pull up I had to pull up my chapter 21 PowerPoint notes. It's the study of alpha carbon chemistry, enols and enolates. But before I do go into that chapter, I'd just like to make a comment regarding the final exam. The final exam will cover, it's comprehensive. It'll cover chapters 12 through 21. So 21 will be on this exam. We're gonna probably get through half the material today. We'll have a shortened lecture today, and then we'll do the other half on we'll get the other half of the material done on Monday, and then we'll see how we are on time with the homework. So based on that, I'll assign homework questions from chapter 21. I'll probably get the homework question for 21 out before. I just need to take a look at it, what's appropriate, what's not appropriate, and how many is a good quantity to have. So I'll get the homework questions out today. So you'll have access to the chapter 21 homework questions. So with that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chapters that we've gone over. So that means we're going to pull 3 questions from each chapter. So you'll have 3 questions from chapter 12, 3 questions from chapter 13, and so on until we get to chapter 21. And you'll have 3 questions from 21. That divides everything equally. So, we have equal parts from equal chapters. It's a comprehensive exam. That I won't pull any questions from chapters 1 through 11, but some of the concepts could be, very similar, to what you've seen in the past, so, but keep in mind that, the test will consist of problems from chapters 12 through 21. We should finish 21 by Tuesday at the latest. And that'll be the last chapter that we go into. Because we won't have any time to do it. So if you want to do the exam over the weekend, you'll feel free to do so. I'm not gonna, if you see some chapter 21 questions, I'd do the homework first just to give you kind of an idea of what chapter 21 is about, and then you can take it from there. But I think that'll be a good ending point for us for this class. To go through chapter 12 through 21. That's 10 chapters. That's a lot of chapters that we covered. So that'll be the plan. Also, I'd like to point out to the extra credit opportunity. Please fill out the survey from both the Google document form and the one that EKU gives out through let me see what they call it. They call it, I'm just seeing what they're calling it. I'm pulling this up. I guess it's just called EKU course evaluation. So that's through Explorance Blue. So you should be able to access that. If you do this, then you'll get the bonus points. Otherwise, then there will be if everyone participates, everyone will get the same number of bonus points. But then there's a percentage of how many people need to present or to participate. So I really enjoyed teaching you. So I'm looking forward to the comments. Especially, comments related to the laboratory, whether you'd prefer the laboratory in person or, online. We're really interested in that. So if you can go ahead and respond, that'd be great. So with that, let's go into the lecture material, chapter 21. I guess so in the beginning, we're going to have a shortened lecture. That way, you can get an extended weekend. You can also, if you have any questions, you can ask that after class, or if you want to study, please use that time to study. I'll probably post the exam sometime tomorrow. I know on the syllabus it says Friday, but I'll probably get it done and posted sometime tomorrow. That way it gives you extra time to get the exam done. I still haven't created the exam yet, so I need to do that. That's on my list. So this is the chapter 21 PowerPoint notes. Sorry about that. Let me go back into it. Oh. New share. Okay, there we go. So we're going to be talking about alpha carbon chemistry, enols and enolates. There's a lot that goes on in this chapter. That's why I wanted to divide it into 2 lectures. I just feel like there's a lot of material with this lecture. So Greek letters are used to describe the proximity of carbon atoms relative to the carbonyl group. Let me get my pen out. A lot of chemistry is going to take place at this alpha position, sometimes at the beta position. So this chapter will primarily explore reactions that take place at the alpha carbon. So this carbon right here. And like I said, there's a lot of material in this chapter. That's why I think it should be devoted into 2 chapters. I don't want to push too much on at once. Otherwise, it's going to be hard to get the material down. Alpha protons are protons attached to the alpha carbon. We saw that this is a great example of where the alpha carbon is. And we're going to cover a lot of reactions by an enol or enolate intermediate. So in the presence of an acid or base, a ketone or aldehyde exists in equilibrium with an enol. So we have this ketone enol. Most of it's going to be in the ketone form. That said the ketone and enol are tautomers of one another. This is the more stable form, and generally, there are special cases where they showed a special case in the book where the enol form was more prevalent, but that was due to resonance, and it was on a ring structure. Let me see what page that was on. Okay, that was on page 956. Where this is the special case where just imagine. No, let's not imagine. There we go. We have this ketone here, and then we have this here. You can see that we have resonance here, right? So even though that we're in the enol form, this is going to be 99.99% more prevalent because due to the resonance right here. So it's going to be on this side. So this is a special case where the enol exists more than the ketone. So there's going to be a lot of reactions that can take place right here. Usually this is the RDS, the rate determining step is going from here, from the ketone to the enol. So there are exceptions, as the example below, where the enol form is favored at equilibrium. Here they give you another exception right here. And that's due to this hydrogen bonding then right here. So it is more stable than a typical enol and is favored at equilibrium. So you have a couple cases. You have H bonding and where you have conjugation or resonance. And they show you the one that I just showed. So the phenol is an example where the enol is vastly favored over the ketone at equilibrium. The phenol is an enol with aromatic stability. And I showed you where that was. This is on page 956. All right. So the mechanism for tautomerization depends on whether it is acid catalyzed or base catalyzed. Here they're showing you an example of an acid catalyzed tautomerization. So we have a proton transfer. Then we have a resonance stabilized cation right here. Followed by another proton transfer, and we get the enol. So here's your enol, here's your ketone. And this is through an acid catalyzed mechanism. So basic, you're gonna have to move my screen a little bit. So base is just kind of similar, you have a base here, it's going to take this proton right there. And they show that on the other slide right here. This is under basic conditions. This is your alpha carbon. So this base takes this proton, it forms a carbanion. It can form this double bond, it's resonance stabilized anion. We have a proton transfer, and we get the enol. So here's your enol, here's your ketone. So this is base catalyzed, the other one is acid catalyzed. So the alpha position in enol is nucleophilic. So once we have this right here, we can see that we can go react this and go take stuff. So with this base, in the presence of strong base, an enolate forms. So enolate is much more nucleophilic than the enol, as it carries an overall negative charge. See, this has an overall negative charge, where the enol, we have this protonated, this doesn't have an overall negative charge. The enolate can undergo carbon C attack or O attack. So enolates generally undergo a C attack, which is drawn one of two ways, depending on which resonance form of the enolate is used. It says most of this chapter involves enolates. So let me see something. So in the book, it says, nevertheless, for simplicity, when drawing mechanisms, we'll often draw the less significant resonance contributor of the enolate, in which the negative charge is on the alpha carbon. That is a C attack. So the O attack would be when the oxygen atom attacks an electrophile, it is called an O attack. So I do a good job. So when the oxygen is attacking, it's an O attack, a C attack from the carbon. Alpha protons are the only acidic protons on an aldehyde or ketone that can be removed to form an enolate. The beta or gamma protons are not acidic. Deprotonation will not yield a resonance stabilized intermediate. It says the pKa values of alpha protons must be considered when choosing an appropriate base to form an enolate. When pK values of the base and enolate are similar, both products and reactants are present in significant amounts. Shows this is an irreversible reaction because we form hydrogen gas right here. So to irreversibly and completely form an enolate, a stronger base must be used, like sodium hydride. LDA is a strong base commonly used to form enolates irreversibly. It is made by treating diisopropylamine with N-butyl lithium. It says when LDA is used to form an enolate, the amount of ketone present at equilibrium is negligible. So that means we're going to be over on the right-hand side. This LDA features two bulky isopropyl groups, which allows it to be a strong base, but not a good nucleophile. I show you LDA right there. So when protons are alpha to 2 carbonyl groups, they are much more acidic. You can see, okay, we're alpha to these carbonyl groups are more acidic than they are right here. The increased acidity is due to the increased stability of the resulting enolate. So you can see that, you know, there's more stability right here, so they'll be more acidic.
And where?
All right. So 1,3-dicarbonyls are acidic enough to be irreversible deprotonated by an alkoxide. So we have that right here. And there would be no need to use NaH or LDA to form the enolate of 1,3-dicarbonyl. It'd be an overkill. So here they're showing you an overkill. All right. So it's important to know what base to use in order to generate an enolate, depending on the carbonyl compound and the desired result, a reversible versus an irreversible result. So here we get both the enolate and the ketone are present at equilibrium. This is an irreversible enolate formation, and LDA is not necessary for this one. It says under acidic conditions, ketones and aldehydes undergo alpha halogenation, and they show that mechanism. So this works with Cl2, Br2, and iodine. Acidic conditions mean an enol is a reactive intermediate. And I show this how this forms on these next two slides. We have a proton transfer to the carbonyl group. This is in resonance. You can imagine if we put these electrons right here, and we have a positive charge here. We have a proton transfer, and we have our enol. And once we have the enol, these electrons, one of the lone pairs from the oxygen can come down, form this double bond, and then, you know, we can have so the enol functions as a nucleophile, so it's going to take one of the bromines, and that's going to release one of the bromines because bromine's a good leaving group. And we have another proton transfer, and now we have our halogenation. So when an unsymmetrical ketone is used, halogenation occurs faster at the more substituted carbon. So you can see right here, it's going to go faster, and this will be a minor product right here. The major product results from the more stable, more substituted enol. So here's the more substituted, more stable enol. Alpha halogenation provides a two-step synthesis for the synthesis of an alpha-beta unsaturated ketone. Other bases can be used. So what happens then is you have this bromine right here, and they're not showing you this. So you get the bromine right here as a major product, right? And then this pyridine is a base. This pyridine acts as a base, and it's going to take this proton, it's going to put this double bond, and this can be released. That's how you get to this product right here. So the first product, so to get to here, you just follow these steps right here, right? You have the proton transfer, you form your enol, then we have the halogenation, and then once we're halogenated, it's going to form on the more substituted side, and that's where our major product comes. And then to form this double bond right here, we just use a base. So the Hal-Vollard-Zielinski reaction brominates the alpha carbon of a carboxylic acid. So that's all you have to know. So if you have these set of reaction conditions, you're going to brominate at the alpha carbon. The mechanism is believed to follow the following sequence, where we have an acid halide enol, followed by our halogenation. Alpha halogenation can also be achieved under basic conditions. So under basic conditions, an enolate is the reactive intermediate. So you have this mechanism right here. Under basic conditions, polyhalogenation typically occurs. That means we're going to halogenate more than one side. But once the ketone is brominated, it forms an enolate and brominates again at an even faster rate. Under basic conditions, methyl ketones are converted to carboxylic acids. So if you have this, with these reaction conditions, we're going to form this carboxylic acid. Then it says, after all the 3 alpha protons are replaced, the CBr3 acts as a good leaving group. So you can imagine this as a good leaving group. And then, we're going to form the resulting carboxylic acid is deprotonated. So under basic conditions, methyl ketones are converted to carboxylic acids. We can see this methyl ketone converted to a carboxylic acid. This is a synthetically useful way to produce carboxylic acids from methyl ketones. It says a recall an aldehyde is treated with a hydroxide in equilibrium forms when significant amounts of both the enolate and aldehyde are present. If the enolate attacks the aldehyde, an aldol addition reaction occurs. So this stands for, you can just imagine aldehyde, and this stands for alcohol. That's how they got the name aldol. The product features both an aldehyde and alcohol groups, and the alcohol group is usually beta to the aldehyde. Does note the location of the OH group, the hydroxy group, on the beta carbon, and that's in the beta position. So under basic conditions, an enolate is a reactive intermediate. So here we have the alpha position is deprotonated, forms this carbanion. The enolate serves as a nucleophile and attacks an aldehyde. So you can see that it's attacking this aldehyde right here. We have a proton transfer, and now we have our aldol. The aldol addition is in equilibrium. For most simple aldehydes, the aldol product is favored. So here's a simple aldehyde. We get the aldol product in that 75% yield. For most ketones, the aldol product is not favored. So you see, we have a ketone here. We have two R groups, and we're only going to see that in 20%. So here is your alpha. Here's your beta carbon. Here's your hydroxy group. Here's your alpha. Here's your beta carbon. Here's your hydroxy group. So taking the aldol and going in the reverse is called a retroaldol reaction. So we have a proton transfer. We have a loss of a leaving group to form this carb anion here. Then we have another proton transfer. And we get two ketones. So an aldol product is heated under acidic or basic conditions and alpha beta unsaturated carbonyl forms. And see at the alpha position, oh, not writing. Sorry. At the alpha position and the beta position, we have an alpha beta unsaturated carbonyl. So this is an aldol condensation because we're losing this group right here. It says an aldol condensation occurs when an aldol addition is performed at elevated temperatures. So aldol condensation occurs when an aldol addition is performed at elevated temperatures. We see this right here. We get the alpha beta unsaturated aldehyde plus water. So they go into this called an aldol addition mechanism where we have a proton transfer followed by this carbanion, gives a nucleophilic attack. Then we have a proton transfer right here. So the resulting alkoxide ion is protonated. Now they talk about the elimination of water. We have a proton transfer. This carbanion is going to come up here, and the hydroxide is ejected to avoid the product. And that's how we get this product right here that we just talked about. That's our retroaldol. That's not a retroaldol. That's our aldol condensation reaction. So sterics are a factor. So when two stereoisomers of pi bonds can be formed, the product with fewer steric interactions is the major product. Here you can see this would have more steric interactions right here. It'd take a lot further to go for this. It wouldn't even happen anyway. So because the aldol condensation is favored, often it is impossible to isolate the aldol addition product. So this is not isolated. But we do get this. The yields for condensation are typically much greater than yields for the addition reaction. Two different aldehydes and ketones react in a cross aldol reaction or a mixed aldol reaction. So two different aldehydes yield four possible aldol products. And cross-aldol reactions are only practical if the number of products can be minimized, which is achieved in one of two ways. One of the substrates is relatively unhindered and without alpha protons. So in formaldehyde, there are no alpha protons, right? If there were, you'd have to have a carbon here, and I'd have to have protons here, and this would be the alpha carbon. But there is no such thing in the formaldehyde. The cross-aldol reactions are only practical if the number of products can be minimized, which is achieved in one of two ways. One of the substrates is relatively unhindered and without alpha protons. It says this is possible when only one compound can form an enolate and the other compound reacts with the enolate faster. And it says the one compound is not isolated. So, this compound right here is called benzaldehyde, right? So the reason why this is not isolated is because we go through a condensation reaction. So if we go through a condensation reaction, we're going to get this right here, this product. It says then cross-aldol reactions are only practical if the number of products can be minimized, which is achieved in one of two ways. Use LDA as a base, directed aldol addition, and one compound is completely converted to an enolate with LDA. The other carbonyl compound is then slowly added to the enolate. So the success of this is limited by the rate at which enolate ions can equilibrate. In other words, it is possible for an enolate ion to function as a base rather than a nucleophile and depronate a molecule of propanol aldehyde. If this process occurs too rapidly, then a mixture of products will result. So then they go to this intramolecular aldol reactions. They form cyclic compounds. Sometimes they won't form cyclic compounds if it's too strained, like a three-membered ring. So one group forms an enolate that attacks the other group. Only 5- and 6-membered rings form well this way. We're not going to be forming 3-membered rings. They're just two rings strained. It says esters also undergo reversible condensation reactions. This type is called a Claisen condensation. This reaction right here was named after a scientist called Claisen. He took this ester under these reaction conditions and generated this in 75% yield. It says Claisen condensation is simply a nucleophilic acyl substitution reaction. And we see this on the next slide right here. So we have a proton transfer. So we have our ester, right? Followed by a nucleophilic attack. It's just the same compound being attacked. We have a loss of a leaving group. We have another proton transfer. Here we have our carbon ion. So it's the last step, the depronation of the beta keto ester drives the reaction to completion. Acidic workup is necessary to obtain the neutral products. There are some limitations to the Claisen condensation. The starting ester must have 2 alpha protons. So if it doesn't, it's not going to work because the removal of the second proton by the alkoxide ion is what drives equilibrium forward. The hydroxide cannot be used as the base to promote clays and condensations, otherwise ester hydrolysis occurs. Just want to it's your alpha, and this is your beta position right here. So at the beta position, you have a keto, and this is an ester right here, right? That's why they call it a beta ketoester. So some other limitation, alkoxide that matches the OR group of the ester is needed, otherwise transesterification occurs. When we come into this study called cross clays and condensation, this is on page 978. They're only useful if one of the following criteria is met. One ester has no alpha protons. And here we don't see any alpha protons here, do we? Perform directed clays and condensation with LDA as the base. And the reason why about the LDA, directed clays and condensation can be performed in which LDA is used as a base to irreversibly form an ester enolate, which is then treated with a different ester. So that's the reasoning behind that. Then Dykman comes out with this cyclization. So intramolecular clays and condensations can also be achieved, and this is called a Dykman cyclization. Like with aldol reactions, Dykman cyclization prefers the formation of 5 and 6 membered rings. So let's just say, for instance, we have this compound here, and we have this here. You can see how we're going to form that ring then. And this would come up here. And this would be a good leaving group. So alkylation of the alpha position, the alpha position can be alkylated when an enolate is treated with an alkyl halide. So the enolate attacks the alkyl halide. This is a concerted reaction, right? SN2. And we add our alkyl group then. So as typical SN2 reactions apply. If you have too much stuff right here, then you're gonna E2 elimination dominates. Regioselectivity is an issue with unsymmetrical ketones. 2 different enolates can form. So this goes on to, if you go to page 21, they show you this reaction diagram, not page 21, page 980. So the more substituted enolate is more stable and is called the thermodynamic enolate. The less substituted enolate is less stable, but is formed more rapidly and is therefore called the kinetic enolate. And that's because the kinetic enolate, you'll see on the next slide, has a lower activation energy. And they show that right here. So this is your kinetic product. This is your thermodynamic product right here. You can see that there's a larger activation energy. But in general, please keep this in mind. You know, it is possible to choose conditions that will favor formation of either enolate. So if you want to form the kinetic enolate, LDA is used at a low temperature. And LDA is a sterically hindered base and can more readily deprotonate the less hindered alpha position. So low temperatures is necessary to favor the formation of the kinetic enolate. So if we have higher temperatures, then we're going to favor the thermodynamic enolate. You can see that right here. Then we come to the study of malonic ester synthesis. And malonic ester synthesis is a technique that enables the transformation of a halide. We have this halide into a carboxylic acid with the introduction of 2 new carbon atoms. Diethyl malonate is the starting material. And here we have a stabilized enolate. Remember, the pKa of this was a lot lower because we sandwiched this in between 2 carbonyl groups. So the malonic ester is a ferric acidic compound. We talked about why, because we have it sandwiched in between 2 carbonyl groups. The first step of the malonic ester synthesis is the depronation of the diethyl malonate. Okay, so we're going to have deprotonation right there, right? This is going to take our proton away. We have depronation. Once we have that depronation, the enolate is then reacted with the alkyl halide. And both ester groups are then hydrolyzed. So one of the resulting so at a high enough temperature, you can have one of the resulting carboxylic acid group is then decarboxylated with heat, gives off CO2. So this is not coming back. This is not going to go the other way because this is going to be gone, a CO2 gas. 1,3-dicarboxylic acids undergo decarboxylation in a pericyclic process. You can see this pericyclic process right here. This oxygen is going to grab this proton, we form this double bond right here. And we have loss of CO2. See, we're forming CO2. When that bond comes here, we're going to have CO2, right? So we're just going to have left with this right here. That's all you see right there on this side. So here's an overall synthesis of this. With this compound here, under these set reaction conditions, we generate this carboxylic acid. It says diethyl malonate can also be dialkylated, which means we're adding 2 R groups to it. So in this reaction sequence, diethyl melanate is going to be alkylated twice, each time with a different alkyl group. Then hydrolysis followed by decarboxylation produces a carboxylic acid with 2 alkyl groups at the alpha position. At the alpha position, we form 2 alkyl groups, didn't we? Here's one, here's your second one, R1 and R2. So the acetic acid ester synthesis is analogous to the melanate synthesis, converts an alkyl halide to the methyl ketone with 3 new carbon atoms. So this process, so the acetic acid ester synthesis is very similar to the malonic ester synthesis, except that the key reagent is ethyl acetoacetate. This is the key ingredient right here. Ethyl acetoacetate. Instead of rather than the diethyl melanate. It says ethyl acetoacetate is very similar in structure to diethyl melanate. And you may ask, well, what is diethyl melanate? Let's see. That's diethyl melanate. As you can see, it's a very similar structure. But one of the ester groups has been replaced with the ketone group, hasn't it? So one of the ester groups right here, we replace it with a ketone. So the first step of the acetic ester synthesis is analogous to the first step of the malonic ester synthesis. Ethyl acetoacetate is first deprotonated. So we get our first depronation right here, forming a doubly stable enolate. This enolate, so we have a carbanion right here, basically, right? This enolate is then treated with an alkyl halide. We're going to treat with an alkyl halide. Let's just use here's the alkyl halide they're using right here. We'll just use this one. See, alkyl halide is just RX. This R group is this right here, that stuff. And that X is the bromine, so it's going to go right here. This is a good leaving group. And this is resulting in an alkylation step. It says then treatment with aqueous acid then results in the hydrolysis of the ester group. So we're going to have hydrolysis of the ester group because of this acid workup right here. So it becomes an OH. So if the hydrolysis is performed at an elevated temperature, that's why they have heat right here. The resulting beta keto acid will undergo decarboxylation to produce a ketone and carbon dioxide. And we saw this right here. So it's going to undergo this right here, where it's going to produce CO2 then. It says decarboxylation can occur because the carboxylic acid exhibits a carbonyl group in the beta position. Which enables pericyclic reaction can occur. So first we're going to deprotonate it, right? And then we treat it with an alkyl halide, followed by an aqueous acid, treatment with an aqueous acid to convert this to a hydroxyl group right here. And we have that elevated temperature. If we treat it again, I think they they show on another, if you go to page 985 where they treat it again, you can have 2 different alkyl groups on there. And then someone may ask, why is it necessary to use an acidic ester synthesis instead of simply treating the enolate of acetone with an alkyl halide? The question is, wouldn't that be a more direct method for preparing a substitute acetone? And there's 2 answers to this question. Number 1, direct alkylation of enolates is often difficult to achieve in good yields. And 2, enolates are not only strong nucleophiles, but they are also strong bases. And as a result, enolates can react with alkyl halides to produce elimination products. So, like I said in the beginning, I think there's a lot of material. So we're going to end right here. We'll finish up on our next lecture. And just please know that, I will get the homework. I'll probably post the homework today. The test you'll have to wait till tomorrow. And I wish everyone the best of luck, and please remember to fill out your surveys. Thank you and have a great day.